We had earlier talked about two class of clustering algorithms. One was the hierarchical algorithm, where we successively either agglomerate, merge together a set of points till we get the desired number of clusters, or divisive, where you split the entire data set into groups till we get the desired number of cluster. And depending on how we measure the distance between two groups of point, we had either the average linkage or the single linkage or the complete linkage clustering algorithm. We also found out that these algorithms can find out any arbitrary cluster shapes, non-convex or any other shape, but they are sensitive to noise and they take a lot of time when run on the large data sets. The other class of clustering algorithms we described was the partitional, where instead of hierarchically merging and splitting points, we in a single go divide points into desired number of groups and then update them. So, it is iterative algorithm. So, in the k-means we start with random initial seed points, and all the points which are closer to a particular seed are put together, and then the seed points are updated by the mean value of all these points that are grouped together. This process continues till the seed points do not change over iterations. So, this is the k-means algorithm. This algorithm, a limitation is it can produce only spherical clusters, and even though the advantage is it is very fast, in few iterations it converge, and it is robust to noise. Today we talk about a third category of clustering algorithms known as the density based clustering. The idea is like this. So, we will discuss clustering. The idea is that if you again I am drawing points in 2 dimension, it can be in any dimension. If you have say clusters like this and like this, then you see one of the way you can define a cluster is a set of points who have lot of other points in their neighborhood, and all such points connected together would form a cluster. So, we look at two things. We study density of a point, that means if there are other points in the neighborhood. For example, this is all these points are dense, but maybe if we have one or two separate points, they are not dense, because there is no other point in the neighborhood. So, we talk about density of a point and we talk about connected points. So, in sense kind of they are connected. I will soon define what this connected actually means. Okay. So, if we define a cluster to be like that and name points which are not part of a cluster as outliers, you can as well have a clustering algorithm. So, the these kind of algorithms are of course called density based clustering algorithms. So, this idea is used in one clustering algorithm called dbScan. Density based spatial clustering, acronym for all that. So, let me explain what it means. I will come back to this. So, how you define density? You define density as points within a specified as points within a specified radius of the given point, that is the density. A point will be called a core point if it has more than some main PTS number of points within this epsilon radius. So, these are kind of points interior to the cluster. And then you have border points which are not dense, but they are connected to other dense points, and the points which are neither core neither border, we call them as noise or outliers. Let me explain you again this concept. So, we draw the figure again. I draw the figure again. Okay, so suppose these are my clusters and there are some outliers. So, how to measure density of a point? Okay, you should think how dense is a point. So, how dense it is? The comes from the intuition. Say you say some public place, say railway station or something, it is very densely crowded, or we say some park is not very densely crowded. So, how do you do? Basically, you look at a person and see a small area around a region around that point, and there is, if there are a lot of other people around lying also standing in that area, you call it a dense spot. So, the same thing we do here. What we do, suppose I am wanting to find the density of this point. What I will do? I will draw an circle centered at that point and with radius epsilon, EPS you can call it epsilon. Okay. Now, usually we take epsilon to be small and we draw a circle of radius epsilon. So, in 2 dimension it is a circle, in higher dimension 3 dimension it will be a sphere, in general d dimension it will be a ball. So, to say that terminology is called a ball. Usually this algorithm will work if the dimension is relatively low, maybe less than 3 or less than 4. Okay. In higher dimension it is not a very good method. So, that is why DB-scan is only applied to, it is originally only applied to geospatial GIS data sets mainly, where you have less number of dimension. Okay, anyway. So, we have this epsilon neighborhood, a circle centered on a point and radius epsilon. And we count how many other points lie in that neighborhood, how many other points lie in that neighborhood. So, other points lie in the neighborhood. And if that number is big, high, relatively high, so how do you do? You check whether this count is greater than or equal to some threshold that we set called mean PTS, maybe 5 or 7 or 9 or something. It is a count integer. So, you see how many other points lie in that neighborhood, and if that count is greater than mean PTS, that means we have sufficiently good number of other points lying in the neighborhood, then we call this point x to be dense. X is dense. Okay. In the DB-scan terminology, a point will be called a core point if it is dense. So, all dense points are core points. So, they are usually points which are inside a cluster. Okay. So, they are to a cluster, but there may be points which are themselves not dense, but they are inside a ball, inside a sphere of another dense point. So, it may happen that there is a dense point, there is another point which is itself not dense, but it is within the sphere of another dense point, it lies in a close proximity of another dense point. Note that the radius of this circle is EPS. Such points are called border points. Okay. And a point which is neither a core border is called a outlier or noise. Okay, it is called a outlier or noise. So, this is clear. Let me explain you this thing. So, here in this case, this blue. So, let me put the definition once first. This is the definition: core, border, noise. Okay. So, if we take these blue points and set EPS to be 1 and mean PTS to be 4. So, this is a core point, this is a core point. This is a core point because if you see there are more than 4 points in the neighborhood. This point is not a core, okay, is not a core, but it is within epsilon of the core. So, it is a border point, and this point is neither core nor border, nor it is itself dense, nor it is within epsilon of a dense, the noise point. Okay. So, this is the idea. So, what I will do is that based on this idea, I will define some terms. So, these definitions I said density is one concept, core thing, another concept is connectedness. xi is dense, there are more than min PTS point in a neighborhood of xi of radius epsilon. Okay. So, this is direct connection. Okay. Clear? So, xi is connected to xi if xi is dense and xi is within epsilon of xi. What it means? So, you can find a series of points x1 to xn, okay, x1 to xn, so that xi this is connected, this and 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 this is connected directly till we end in xj. Okay. So, that is the criteria. Connected means this is dense and this is within epsilon, this is dense, this is within epsilon, this is dense, this is within epsilon. Okay. Right. All right. So, this is clear. So, this is how we have connected, first directly connected, then path connected. Now, let us see this, how this helps in clustering. let me first define I am in path connector. I will explain soon. That means you see all the points here, there is a dense point and they are connected to each other, that exists path. Similarly, all are connected to each other, all are connected, outliers are not connected. Okay. So, points. All right. So, these are one equivalence class, one equivalence class, one equivalence class. These are single. Okay. So, this is written down as an algorithm which is like this. The steps you can go through for each of the core point cluster, add them up, reachable, then remove them, cluster the rest, remove them, cluster the rest, till we left to only the noise. Okay. So, example of that, how we get this. Okay, core, border and noise. These are the noise, these are the clusters. Sorry. The clusters. These are the noise. Okay. So, you can see you can get arbitrary separate cluster, but this will work only when you have okay. So, you can get arbitrary separate, it is resistance to noise also, because noise are separated, but this works only when you have low dimensional points, high dimension it does not work. Okay. So, also it works when the density is widely varying, it does not work. Some parts are very dense, some part are, you cannot set a min PTS properly. All right. So, in these two cases it does not work. Okay, so there are different ways of estimating a good mean PTS EPS that I am not going through. So, this is the summary of the DB scan. So, that is the thing, it works well for arbitrary cluster. Noise does not work when there is high dimensional data varying density. It is very much used in spatiotemporal data analysis and low dimensional data, and where you want arbitrary separate cluster. Okay. So, with this I stop there are many modifications to DB scan which people have tried different ways, but this is the basic idea. So, with this I stop this lecture. In the next class I will elaborate on how to evaluate clustering algorithms. Thank you.